Hey guys, so it's time to do some learning, or I should say relearning, about phase diagrams. Now, you've learned about phase diagrams before, that's why I say relearning. We learned about them last year in honors chemistry. Essentially, they're a diagram, a graph, if you will, that allows us to look at what pressure and temperature combinations give a phase of a substance. So, for example, water. We know that water at room temperature, so, around 25 degrees Celsius or so, and at our normal atmospheric pressure, which is around 1 atm, a little less, but let's say 1 atm, we know at 25 degrees Celsius and 1 atm that water will be a liquid. Okay, we know as we lower the temperature, if we get it below 0 degrees Celsius, we know it will become a solid. We know that if it's above 100 degrees Celsius or 100 or above at 1 atm, that it will become a gas. That information we're used to because that's part of our everyday life, but we can actually tell what phase a substance is going to be in under any pressure and temperature combination if we're given a substance's phase diagram. And every substance has its own phase diagram. This one here is just a generic phase diagram, okay, just so that we can go through the different pieces, but every substance has one. And again, this one isn't for any one in particular, but just gives you the basic idea. So in a phase diagram, first things to note are that you have the y-axis pressure and the x-axis temperature. And so we're graphing that temperature versus that pressure that we have, x-axis versus y-axis. We also have regions. So the region that's to the far left is always going to be the solid. The middle area is always going to be the liquid. And then here they use the word vapor, of course, meaning a gas. And then the other important thing to note is that if you are right on the line, anywhere along this line, or along this line, that was terrible, then you are dealing with two phases at that point. Sorry, that's going to bug me, so I'm going to fix it. You're dealing with two phases at that point anywhere along those lines. So like let's say I was here on this line, I would have a phase change between solid and liquid going on. If we were going this way in temperature, if we were increasing kinetic energy, it would be solid becoming liquid. If we were going this way, it would be liquid becoming solid. But if we are on the line, we have two phases. So if I'm right on this line, that means I'm in between a liquid and a gas, so I have both phases present. Say I'm down here, that means I'm in between a solid and a gas. Now you know all of your phase changes. You've learned all your phase changes before. If we have a solid becoming a liquid, right, we know that that is called melting. If we have a liquid becoming a solid, we know that's called freezing. If we go from this box into this one, or this area into this one, liquid becoming gas, we know that's evaporation. Gas back into liquid, we know that that is condensation. Solid becoming gas is sublimation, and then gas becoming solid is deposition. Probably deposition, that last one's probably the one that people are least familiar with, but obviously all are important. Now there's a couple other things on the graph that are important to note. Obviously if I gave you a problem and let's say I told you that you were at this pressure here and this temperature here, you would just follow the lines, the marks over, and see where the line fell. It falls there in that solid region, so you'd know your substance was a solid at this pressure and temperature. If I gave you this pressure and this temperature and had you follow them across, you would tell me that your substance was a gas at that pressure and temperature. So you can tell a lot by looking at these graphs. Again, like I just said, there is some other really important parts to the graph. Let's just take a quick peek. Let me give myself a clean canvas here. So if you take a look, at this point right here. This point right here is called the triple point. Okay, the triple point. And the triple point is where all three phases will coexist. Okay, so you'll have gas and solid and liquid all interchanging at the same time, which is very unusual. You have probably never seen this occur. I would say, not probably is not even right. I've seen it happen because I've seen some demonstrations, specifically using carbon dioxide, dry ice, and putting it under really high pressure situations. I've tried to regenerate that experiment and I haven't had that much luck. That's why I don't show it to my students. But triple point is not something that's common. And when we look at the graph specifically of a couple of things, you'll see why. The temperature and pressures usually are unusual, and that's why you won't ever really see that occurring. You will see, obviously, solid becoming liquid, liquid becoming solid, and all of those changes, just not that triple point area. But know that it exists. Every substance can be anywhere on this graph as long as they're under the right temperature or pressure conditions. Oh, man. Give me a second. Got to figure out how to get back to where I was. Here. There we go. Sorry about that. New computer. The other point I want you to see is this point right here. This is called the critical point. Now, the critical point is a point where you have so much energy in your gas. Your particles of gas are moving so much that once you get past that temperature and pressure, you can no longer liquefy your gas. So you'll notice this leg of this graph right here ends right there. This one goes on indefinitely, but this one ends there. You get into kind of a strange region up here. It's got a defined name. We're not going to really get into it. It's not anything that we're going to have to worry about. But realize that there is a point where your gas particles have too much energy, that we cannot force them close enough together to make their intermolecular forces work. And that's what the critical temperature and pressure or critical point is. Now, what we're going to do next is look at some specific graphs, and you have these ones on your paper. I think yours look a little bit different, but they're the same basic graphs. What I want you to see here is the difference between these two graphs. So we have the graph for water, and we have the graph for carbon dioxide. And you can see, as long as you have the right temperature or pressure, you can make water a solid, a liquid, or a gas. You can make carbon dioxide a solid, a liquid, or a gas. For those of you that don't know, carbon dioxide is dry ice, just so you have more of a visual of what you're thinking about. I know a lot of people think of it in the gaseous state, but you've had experience probably with it in the solid state as well. Now, looking at these graphs, you can see all sorts of things. Like the other day we learned about normal boiling point, right? So normal means the pressure is 1 atm. So here's 1 atm on the water graph. If we go over and follow this line, this right here would be the normal boiling point for this liquid. And you can see that it happens at 100 degrees Celsius. So the pressure and temperature at which water boils under atmospheric pressure, of course, 100 degrees Celsius and 1 atm. You can see over on the graph on the water and the graph on the CO2 where there are triple points are. So find water's triple point would be right here. So water has a triple point at 0.006 atm. That's a ridiculously low pressure. I mean, you're never, ever, ever going to see the triple point of water because you can't get a situation like that in everyday life. The temperature is not so terrible, right? That's just a cold temperature, but it's the pressure that's the limiting factor there. For carbon dioxide, you can see why I said before I've seen it happen, because the triple point for carbon dioxide happens at 5.1 atm, which is 5 times normal atmospheric pressure. I mean, that's a lot of pressure, but it's a pressure you can create. And then the temperature is negative 56.6 degrees Celsius. So very cold, but still reachable. But again, you're probably not going to witness that yourself. So you can see those triple points there. Really what I want to point out on this graph is something completely different, and that is what's happening with a line. If you take a look at this line right here on this graph, you can see it mirrors the first graph that we were looking at. Okay, it looks just like that one. You see that slope of that line. Take a look at the slope of the same line on this graph. On this carbon dioxide one, it is going up and to the right. In other words, it's a positive slope. In the in the water one, it's going up and to the left. It's a negative slope. It's very unusual, and it's very special, and it only happens in water. Okay, only happens in water. And the reason, in water. Okay, the reason for that is water's very unique. Water has a very unique structure that allows it to, and you've probably witnessed this before, I assume you've witnessed this before, most liquids, when they become solids, become more compact. So if you have a liquid and it becomes a solid, it takes up less space because solid particles are supposed to be closer to each other than liquid particles, and they are. Okay, so every substance in the world that happens to, except for water. Water is extremely unique, and its structure is unique, and it's very electronegative, and it has hydrogen bonding forces, and it has all these special characteristics that allow it to do something really, really special. And that is that its solid phase is actually bigger, takes up more space, more volume than its liquid phase. And I say you've witnessed this before. If you've ever put a water bottle in the freezer and seen how it puffs out or the cap pops off, because your particles are actually expanding. That makes no sense at all. That is not logical by the rules of everything we've ever talked about, except again that water is unique. The best way I can describe it to you, and the quickest way I can describe it to you, is that a water particle, let me get a little space here for myself, a water particle is bent, right? So we have our H2O, like so, in our H2O. So our water particles bend like this. And when it's in the liquid phase, the particles have more mobility. They can kind of move around and do their own thing. And so you might get water particles sort of fitting in each other's spaces, like what I'm drawing here in this diagram. You know, they're just kind of all sort of intermingled, moving around of each other. When they become a solid, they become very structured and very rigid in how their molecules set themselves up. I'm going to represent the water with a little line like this to represent the shape of that bent shape that it has. So you have your water particles, and what ends up happening is that they end up lining themselves up in order to maximize their interactions. Okay, and you end up with this very rigid type structure, if you see what I'm drawing here. And they're no longer able to take up those empty spaces that over here they were occupying all that empty space. And so water actually expands because of that. And again, it has to do with its extremely strong polarity. It has to do with its hydrogen bonding forces. It has to do with some things that we won't even discuss, but it's very unique. So that brings us back to this graph, and the reason why this graph is the way that it is. Again, let me clear this off for myself so that I can show you here. What you'll see, and this, again, we talked about ice skating the other day. We can go back to that again. When you put pressure on water, because it's in that structure that's very rigid and has lots of space, as soon as your ice skate comes along and starts pushing down, it will force the particles back into each other's spaces. And when they're in each other's spaces, that's when they're a liquid. So putting pressure on a solid piece of ice actually causes it to liquefy. And that's not true of anything else. Everything else just becomes more solid. And you can see it on the graph here. So let's say I am at a solid CO2, say at this temperature and that pressure. And I keep the temperature the same, and I just put increased pressure, okay, like I'm ice skating on it. Nothing's going to happen. It's going to still stay solid. Even if I'm here and I push on it, if I'm here, I push on it. Notice no matter where I am, if I keep temperature constant and I push on it, it just stays solid. But watch what happens with ice. Now, if you've got it cold enough and you push on it, nothing happens. But come over here. Let's say we're here at this point A that they have, and we put pressure on it. We put pressure on it, and boom, all of a sudden, it went from being a solid to being a liquid. So as long as you're in the right temperature range, sort of in this range in here, you can actually liquefy your solid. And it's special and it's unique, and that's why its phase diagram looks like this. The AP test loves to ask the question about these phase diagrams. They'll show you two of them. They won't tell you what the substances are. They'll show you two of them, and then they'll say, which one is water? Or how do you know this one is water? And it all has to do with that negative slope, indicating that you can put pressure on it and cause it to liquefy, which means it's obviously a unique substance. Okay, so phase diagrams, you should be able to tell pressure and temperature, what phase your substances are at. You should be able to identify triple points, critical points. By the way, here's a critical point and critical point. You should be able to, what else? Find the normal points, the normal boiling point, melting point, etc. on a substance. And then obviously understand this idea of the uniqueness of water. And water is the only one who looks like that. Okay. All right, a couple other terms if you want to take a look at these. Surface tension, you can see I'm using my Spanish curriculum here for you on my diagram. I couldn't find one in English, but oh well. Surface tension you've all seen, that's when the little bug is sitting on top of the water and he's not breaking the surface tension, yet if you tried to sit on the top of the water, you break the surface tension. That all has to do with intermolecular forces, and I think this diagram really shows it to you well. You see you've got your particles. Let's say the particle that we're talking about is right here in the middle of this, and he's attracted out to particles all the way around him, okay? But up here, the water particles that are right at the surface, they're only attracted to the ones to the side and down. So there's more force acting to the side and down, and it ends up forming, it says in the definition up here, like a skin-like layer. It ends up forming like a barrier. I like to think of it like Red Rover. These guys are up here, all the guys that are playing Red Rover, and the water particles are trying to bust out, right? They're trying to overcome those intermolecular forces to become gases. But this skin-like layer is stopping them from doing that because they're exhibiting force to hold the particles in. And it's the reason why, if you look over at this picture, you see that bubble-like formation you have. I mean, it's not like there's something on the outside there. That's all just water holding itself in. It's very, very awesome to see. And this type of thing wouldn't happen with something that had just regular dipole-dipole forces or had LDFs because the intermolecular forces aren't strong enough. Or this picture here is kind of hard to see, but it's a paper clip floating on top of water. Same thing. It's got enough, there's not enough force forcing those intermolecular forces to be broken. So I think it's kind of cool. The stronger the intermolecular force, the stronger the surface tension, because the stronger this bond is going to be, I use the word bond, bad me, the force is going to be towards those other particles. And then we have viscosity. Viscosity is the resistance of a liquid to flow. So I have a picture here of maple syrup. Maple syrup has a high viscosity, although maple syrup's not a pure substance, but still you can use that term. So something, you can think of things, liquids that are thick as being things with high viscosity, and then liquids that are thin have lower viscosities. Now, it says here water has a low viscosity, but you got to be careful. I mean, if you're comparing water to another pure substance, like rubbing alcohol, for example, water has hydrogen bonding forces, and rubbing alcohol has dipole-dipole forces. So water's actually stronger, and therefore it would have a higher viscosity. So it's all a matter of what it's being compared to. Really what we need to do is think about this, is that viscosity is determined by intermolecular forces if we're comparing two things to each other. So like hydrogen bonding forces are going to have higher intermolecular, I'm sorry, where they're the higher intermolecular force, they're going to have higher viscosity. And then LDFs are going to have the like weakest, not weakest, but thinnest, lowest viscosity out of those. Okay, so again, it's all relative. It's all about what you're comparing to each other. All right, so that should be it. That's actually the end of this unit, but you really need to make sure what we are looking at with this phase diagram, you see the connection back to intermolecular forces. That the reason why we undergo these phase changes and the reason why their phase diagrams look the way they do is all based on how strong their intermolecular forces are.